Okay, today we will talk about the atom. Okay, so the word atom comes from the Greek word which is atomos, which means indivisible. The idea of indivisibility is that if you, let's say, you have a rock like this, and then you cut it smaller, you crush this rock, it becomes smaller rock. And then you crush it again, it becomes sand, and then if you crush it again and again, it becomes smaller and even smaller, until one point that you cannot crush it again. So that point is what we call atom. So that's what does it mean by indivisibility. But the Greek philosopher that come with this idea of atom that is indivisible, they don't test this experimentally. They don't see the atom. So they just use their logic, because for them, logic is enough to sort of like solve the natural mysteries. This is what the idea of previous Greek philosophers and like Aristotle and so on. So they use logic and make a premise, and then they think that this is enough to prove something. But we know nowadays that logic is not enough, you need to prove. Theory is not enough, you need to prove. Okay? So if you fast forward to modern days, like now, we all know, we take it for granted that everything is made, not everything, almost everything are made from atom. For example, let's say you see the gold bar there, and also this is the coal, charcoal, the charcoal. So we know this gold bar and the charcoal was made from the atom. I mean, the sort of like the basic unit for all this is atom. But the question is, if gold and coal, can you see, Rafiq? Can you see this? Okay. If gold and coal, charcoal, are made from the same basic unit of atom, why they are so different? Okay. Bonus mark, bonus time. Okay. Answer this question. If gold and charcoal here is both made from the atom, why they are different? Anyone? Different element? Different element. What is element? What is element?
Like a different chemical.
Sorry?
Like a different chemical.
Different chemical? You don't open this thing,
Different number of moles.
Wait, I need to open this thing. Oh, dah open. Okay. So different number of, sorry? Mole. Okay. So I cannot give mark for those who are not right. So siapa nama? Panjangnya. Akil. Akil. So you said made from apa? Made from element. And then I asked Ceradi. Ceradi? Not Ceradi. You are Amani, right? You said what?
Different chemical.
Different chemical. Different chemical, different element. Made from different element. So Irfan. Akil. Sorry, I'm still memorizing your name. So different chemical. If you answer like that in the, for example, in the quiz or in the what we call in the midterm final, that doesn't give you a full mark, because different chemical doesn't mean anything. Because of course you know it's different. You need to elaborate further. That's what I mean lah. So different element. That's right. But at least you need to tell what is the element means. Because you can say different element, but then the examiner will think, then what is element? So you need at least continue further. Okay. So that's how I tell you how to answer my question lah. It's not enough to have a keyword. You need to explain a little bit further. Okay. So for Akil, Irfan. Akil 0.5 not full . What's your name? Amani. Amani 0.5 not full . That is what's your name? Just now you say what? Different? Different number of mole is totally wrong lah, so I cannot give mark for that . Mole is a different thing . Different number of mole. That's yeah, we will talk about mole later. So the reason why they are so different, like like Akil said, that they are made from different elements. So it means that not all atom is similar. Atom is different. For example, there are small atom, there are bigger atom, there are bigger atom. So that's what makes them different. So so let's see this PT table. So predict table. So let's see. Let me bring here first. Okay, so there are one website that is good for you to look for, which is ptable. Ptable. So this website is basically interactive periodic table. Okay, so you can see this, interactive periodic table. When I say interactive, what does it mean? Is that if let's say I want to find which is metal, so they just highlight the metal only. Okay, if I want to highlight the metalloid, something that is between metal and non-metal, this table will highlight this only, and so on. If let's say I want to find this, sort this according to the mass, so I just go to the weight here, and then you can see this is in terms of mass, this is very heavy lah. So it's interactive. Even you can also see what? You can also see discovered. Okay, if I click discovered, and then I put here the first thing that human not discover, meaning that they know the structure, what's inside that is iron and copper and zinc and so on. So that's why the first they still in this 2000 before Christ, they don't know yet what inside the atom, but at least they know this is iron. So this what does it mean by the year here 2000B. If you cannot see lah, but those at the back maybe you cannot see, but along the way you can see this periodic table is filled up. So it's not like the element here. When I said element, this is different element. Element mean the atom that is different. For example, just now I said there are some atoms small, there are some atoms bigger and bigger and bigger. So that is element. So for example, gold atom here, this gold is basically composed of gold atom, which is, let's say, this big. This magnesium, what we call magnesium element, is composed of magnesium atom, maybe smaller than that. Okay, so that's why not all atom is the same. So if let's say the compound composed of the same atom, same kind of atom, we call that element lah. So you can see this periodic table. If I slide this, what we call this here, you can see the element is not found in one go. What we call slowly and surely, this periodic table is filled up. Okay, so you can see over there. You can see. Okay, so like that you can play around this thing lah. So go to this PT table. Okay, P table. For those at the back, maybe you cannot see that. Okay, so coming back to the slide. Where is the thing? Okay, where is the thing? This thing. How to do that? Okay. So that's the answer for this, because different atom, not all atom is the same. Okay. Now, before we talk about periodic table itself, let's discuss about the atom itself. What comes to your mind when you heard the word atom? Normal. What comes to your mind when you heard the word atom?
The smallest.
Small particle. No, I mean in terms of image. Image. What image that come to your mind when you heard the word atom? Small? Sphere? Like ball, like this. That's ball. Okay? That's all. This thing. Small like that. Okay. I believe some of you might see something like this lah. Okay, there are some nucleus in the middle and then something whizzing around the thing. Okay, so this is just like a Greek time. Atom is smallest thing, but now it's a modern day. Most of the time will see when people talk about atom, something like this. They have like something in the middle, and then they have what we call something whizzing around that. Okay, but this image is quite misleading. It's quite misleading. First, about the electron. The electron, in reality, you cannot see it. Of course, you cannot see, but you cannot determine where is its exact position and speed at the same time. Okay. For example, what I mean by that is that, for example, this ball, right? If I throw it to the arcade, okay, take. Okay. So, okay, come back. Okay, the reason why Akil can sort of like catch this thing is because Akil see this thing, the momentum, the speed, and also the location at this point. So you can calculate that using what we call projectile motion. In the high school, you learn about this physics, the projectile motion, half whatever this thing. So that is classical physics. But when something goes small, like the electron, very small, the physics, the classical physics break down. You cannot predict where is the thing. You cannot find it because they use this different type of physics, which is quantum physics. Okay, it's more about probability. So the more accurate representative for the atom is more or less like this. Okay, more or less like this. So you can see the 1s there, 1s. You can see in the middle there. I don't have the yeah. Oh, I have this, right? I don't know. I have this thing. So you see the 1s there. So you can see the atom in the middle there. They are like a nucleus. That's fine. Okay. But what I want to tell you now is about the electron thing. So you see the electron here whizzing around. It's not like this. You cannot see it. So it's more like this probability cloud. This probability cloud means is that the electron most probable to be found here, around here. Okay. It might be here. It might be here. It might be here. It might be there. So the scientists don't know where, but they just come up with this probability wave function. So that they said that, okay, they are electron, but where is the electron? We don't know. But we can say almost for sure the probability of the electron can be found around this region. That's what this means by this probability wave function lah. Okay. And then for this electron, we talk about electron first. They follow some principle, Heisenberg uncertainty principle. So this is what I said just now. There are some guy called Heisenberg. They said that you cannot determine the exact location and speed simultaneously. That's why, for example, let's say I throw this to Akil, maybe Yasmin got that thing. Suddenly it goes here, suddenly it, what we call, they just sort of like magic lah, appear there, suddenly. So that's what does it mean. You cannot determine the exact location and speed simultaneously. You cannot predict the thing. Hence, this thing, the probability cloud. That's the first thing, first principle. Second principle, the atom, this, what we call this image is wrong at many levels because the electron itself is not like the hard ball whizzing around the thing. Because the electron, in order to this electron to satisfy this probability cloud, you need to view electron not as a particle. Particle is like this, hard ball, right? A particle. So you need to view the electron as a wave, and also the particle at the same time. That is quite weird lah, but that is quantum physics. Okay? Sorry? So the idea is that the electron, so particle wave duality means that when the electron become the wave, the electron can only occupy at certain orbital. So this what we call this, we call it orbital. I believe most of you take chemistry before, right? Have you heard about orbital? Yes. Okay. So electron can only occupy certain orbital. For example, here or here or here or here or here or here or here lah, and not between the orbital. To explain this further, let's see this thing. Okay, let's see this, what we call this periodic table. In this periodic table, you can go to what we call the electron part here. So I don't know those at the back can see or not. So you can see if I click hydrogen, look at here. So as I explained before, the orbital is like a sphere, right? It's like a round circle, but imagine in 3D, it's like a sphere. So this, what we call like the probability of the electron can be found here inside this. Okay, so that is H1. So here, this orbital is sort of like energy level. Imagine electron can occupy certain energy level lah. So if you look here, look the picture here. Look the picture here. Okay, hydrogen, you can see that big. Okay, when I go to helium is the same size. It's more or less the same size. Because, for example, why? Because along the periods, what does it mean by period? Is this a row? That is periods. That's why they call it periodic table. Period. This is period, the row, and this thing is column. Okay? So because hydrogen and helium stay in the same period, so the energy level is same. Okay? So that's why the thing. Now look here. I have this thing. So look here. Can you see Yasmin? Nampak? Nampak ni? Tak nampak? Okay. If you look here, this thing, number 1, period number 1, so you can see there are 1 electron. If I click at hydrogen there, you can see only 1. Only 1 here is filled, meaning that 1 electron is filled this thing. There are 1 electron whizzing around here, When I go to the next thing, you see they are like the same size, but then it fills the what we call this energy level lah. So this is what we call the S block. The S block. The S, and then the yellow here, we call it D, and this is P, and then this is F, SPDF, SPDF. So SPDF is basically like the energy level lah. So meaning that you need to fill in the s orbital. The electron must fill in the s orbital first in order to go to the d orbital, p orbital. Because if you look here, this thing, the lowest energy level is 1s. So any element must fill in the electron here first before it goes to 2s. If I go to the boron, boron is hydrogen, helium. Number 3 is lithium. So I go to the lithium, you can see the size is become bigger. Okay, the blue one, you see the red one is here. The 1s is here. Kan nampak ke tak ni? Atau you saya saja buat nampak? Boleh buat? Boleh. Tapi macam mana nak guna? So you see like this so you see. Okay. So you can see the hydrogen, the first S is like ball. The second helium is also the same energy level, meaning that 2 electrons can stay there. 2 electrons can stay in this probability cloud. So after 2 electrons is filled, they go to 2s. So that's why the third thing, lithium, is 2s lah. But 2s, if you look at 2 is higher than 1. It's higher energy level. That's why it's bigger. So where is the rest? This thing, the previous one, this 1s is this here in the red one here. So meaning that there are 2 electrons inside this, and then there are 1 electron whizzing around this what I call the blue sphere. And then if you go to the beryllium, what do you think will happen? Same. It will be same, but now the different, there will be 2 electrons whizzing around here. Okay, now after this, after 4, you will go, alah ni malas ni. After 4, you go to 5. What do you think will happen when you go to 5? It will become something like that thing, strange thing, like dumbbell, like a dumbbell there, like a dumbbell. Because why? Because the different, let me check here. Because if you look, alamak dah kecil dah macam ni. Because the s orbital is like a sphere, the p orbital is like a dumbbell. Okay, but dumbbell can move like 3 orientation, the x, y, and z. So you have this level, and this level. The p, normally you can fill in each orbital 2 electrons. So you have 1, 2, 1, 2, 1, 2. So like that. So that's why when you go to p orbital, it becomes like dumbbell. So let's go back to this thing. So if you look here, you might ask, where is the s? So the s is merged somewhere inside. Okay, somewhere inside. Because remember, this boron, if you look at this electronic configuration, they have the 1s, they have 2s, and they also has 1p. So meaning that they also have the s, and now have the p. But the p is higher level in terms of energy. That's why you see the bigger one. So the S1 is somehow here inside lah, or merged like that. So that's why you cannot see. Okay, and you can see now the P, you have 3. 1, 2, 3. The color apa ni? Green The green. Itu coarse. Yeah. turquoise, you can see that you have three, what you call three square, three box. And each box you can fill 2 electrons only. Why 3 box? Because just now I said that the dumbbell can go in X direction, Y direction, and Z direction, right? So that's why you get that lah. If you go to carbon, they sort of like different direction, but then you can see this thing goes here. They doesn't fill this first, they go here first. Okay? They need to fill one first, and then to fill to complete the what you call the pair letter. Okay, if you go to nitrogen, you will see like that. Okay, it's fill the term and see the image is change the direction. And then if you go to oxygen, yeah, it just same, but you look, this thing is keep filling up. Okay, and then you add more neon, so you get something like that, meaning that it's just combination of all the thing that previously. Now, when you go to here, sodium, when you go to sodium, Na sodium, what do you think will happen? What do you think will happen if you go to sodium here? If I click here, what is the image will happen? It will become like a spherical. Because why? Because let me click first lah.
Because there's 3s.
Okay, because it's like a spherical, it's bigger. The one that is like dumbbell just now is inside that. So meaning that this sodium, they have all the electron inside previously, and then you add 3s. 3s is bigger energy level. If you look this energy level, you can see 3s is higher than 2p. So that's why it's bigger. Okay, and then you go to magnesium and so on lah. So that is basically the orbital lah. Orbital is basically the energy where the electron can fit lah. So normally in organic chemistry, you just deal until S and P only. SP, S and P. Because organic chemistry, later on you learn just now, I think you learn now, right? Organic chemistry. Organic chemistry is basically about this thing only. Carbon, nitrogen, oxygen, fluorine, chlorine, bromine. Okay? So that's organic chemistry plus the hydrogen. So normally in organic chemistry, when they talk about the bonding, hybridization, they talk about the SP hybridization. S and P. SP hybridization meaning that the energy level of S hybrid with the P. Like this lah, the hybrid ni. The hybrid lah, the hybrid. So that's hybridization. What does it mean lah? Okay, if you go to D, we will not discuss further lah, but the D, if I click the D orbital, it's just like strange thing. The strange stuff and whatever the thing. And then you have this, if you go like, going down like this is just more strange, and then let's say I go to plutonium here, the image is much more like crazy. So it's like, this is just showing where is the electron can be found. That's all. Okay? Okay. So if I go to, if I go to orbital, okay, image, what is the image cantik sikit? This thing. Okay, if you look for this image, you can see the S is like a sphere. The S is like a sphere. And then the P is like the dumbbell. The D, I don't care. The 4, I also don't care. Because your part, you need to at least good in S and P, because that is organic chemistry where most of the reaction that everyday life that. So D and F, just you need to know this is strange. The most important thing you should know is this. The S can fill up 2 electrons. The P, okay, so this is energy level. So these 2 electrons, 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 and so on. So meaning then this, here, the maximum it can fill is, for the S is 2 electrons. For the P, the maximum it can fill is 6, because there are 2 here, 2, 2. The maximum for D is, you calculate yourself lah. Okay, 2 times 1, 2, 3, 4, 5. 10 lah, 10. So that's why if you look here, if you look there, you can see here, the D, they have 1, 2, 3, 4, 5 box, and then there are 10 electrons, and so on. So that is orbital. So this is, that is what does it mean by orbital lah. Okay, so let's look here, blah, blah, blah. Okay, Heisenberg uncertainty principle I already discussed. Particle wave duality I already discussed. Okay, Pauli exclusion principle. This is where only 2 electrons can occupy per energy state. That's why one energy state, the S or P or whatever, only 2 electrons can occupy that because of this principle, Pauli exclusion. Okay, and then the Han rule, every orbital in the sublevel is singly occupied before any orbital is doubly occupied. The easy understanding is that if you look here, if I put here, you can see that like this lah, like this, carbon, let's say carbon. So you can see carbon. They doesn't fill 2 first. They must fill 1 first and then go to the next orbit, next suborbital, fill, and then they fill that, and then only then they can filling the 2 there. So if you look there, the carbon and then nitrogen and then oxygen, and only then they come back to fill in. So that is Han rule. So this is basically Han rule lah. Mana? That is Han rule. Every orbital in a sublevel, for example, p orbital, they are sub, right? For example, p like this, p x, y, z, is singly occupied before any orbital is doubly occupied. Okay, understand or not? Okay tak? Okay. Okay, apa lagi nak cakap? And then SPDF, just now lah, they just the how it's shaped lah. Okay, next. Okay, next. Okay. So this is about electron. So let's see what inside this thing. So you can see there are proton, there are neutron. Proton and neutron make a nucleus lah. So inside the atom. Wait. Okay, Bohr's models. The one that we just see just now, the what we call the electron cloud and so on, is so difficult to. Let's say I want to teach you about this electron moving here and there. It's so difficult to teach if we use the orbital representation like the cloud and so on. So that's why the Bohr's models come. So it make scientists easy to explain to other person lah. So the Bohr models is like this. Instead of having this like shape, weird shape of orbital, they just make like an orbit like that. Okay, this is the S. So you can see the SF2, and then this is the P. Okay, P. This is carbon. This is carbon. You can see carbon. If you look at the periodic table, there are 6 proton. Okay, when you see the carbon, where is that thing? Here. So when you see the carbon here, let me make it. So you can see properties. If you look carbon here, okay, so it's carbon here. Carbon here, this 6, meaning that carbon have 6 proton. Okay, carbon have 6 proton. If you see here, if you see gold here, gold, this is gold, aurum, 79, meaning that they have 79 proton inside. Proton is what in the middle lah. So if you look in this picture, where is the picture? This is difficult. How to? Oh my thing. Where is the thing? Okay. So you can see. So this is carbon. Proton is the one that is positive. So you can see 1, 2, 3, 4, 5, 6 proton. And then the Bohr's model, they said that the electron occupy the specific orbital like this lah. Instead of represent in the like dumbbell shape, the sphere, they just simply make an orbit. So electron is what matter in everyday chemical reaction. Meaning that when you see a reaction, when you, for example, light a candle or do something, what make that happen is because of the electron, especially the electron that is in the outer shell, outer orbit. We call it valence electrons. Outermost electron, we call it valence, valence electron. Valence electron. So when electron moving, that is where chemical reaction happen. Okay, this thing in the middle, rarely involved in any reaction unless that reaction is so bombastic, so powerful, so like that lah. For example, let's say in the sun, fusion. Okay, fusion meaning that what we call bercantum lah, like bercantum lah, combine. For example, fusion in the sun is basically helium. So helium is basically two proton. This two proton. This is helium. Hydrogen is basically one proton. So in the sun, what happens is that one hydrogen atom, they go find another hydrogen atom, and then they combine. They combine like this. So that is fusion, and this is hydrogen. They find another hydrogen, still hydrogen. It become helium. This different thing, helium. Okay, it become helium. Hydrogen plus hydrogen, it become helium. Okay, this thing to happen, to merge two protons together, is not easy. You need a lot of energy to do that. In sun, yes, it can happen because a lot high temperature and also pressure. Okay, and also fission. Fission is basically the breakdown of the sort of like of the nucleus. Nucleus. So if you have something like this, and then it break down, something like this, become like this. So that is nuclear fission. Okay, so it's break up. Remember, this electron, this proton, this nucleus is tightly bound. When you break it, you need to use a lot of energy. It will release a lot of energy. When you want to combine it, it needs a lot of energy, like in the sun. When you want to break it, because a lot of energy is needed to make it like a nucleus, when you break it, a lot of energy is released, like a nuclear bomb. So that's why in everyday life, most of chemical reaction that you do is related to the electron only. Electron move here and there, that is chemical reaction happen lah. Okay. So there are also another model called Lewis model. Okay, Lewis model just show the outermost electron, which is the valence electron. Those at the outside here is the valence electron. Carbon have what we call 1, 2, 3, 4, 5, 6 electron. So we know that the first s orbital can fill 2 electron. That's why you get this is fully occupied. That's why the electron need to go to another energy level. The next energy level is P, sp. So the P, we know that the total electron that can occupy the all P orbital is 1, 2, 3, 4, 5, 6, right? But only 4 is filled now. So meaning that this carbon has the ability to receive something, because it's not fully yet what you call it can combine up with other lah, because the outside the valence electron is not yet octet, not yet full lah. So that's why it can combine with other stuff. Okay, so that is the thing. And Lewis model is just showing the what we call the valence electron. This normally you use in the chemistry, organic chemistry, to simplify the thing rather than to draw all the stuff here inside which is not relevant. You just draw what is relevant, which is the outer electron, just to show that this is what is important in chemistry, the outer electron moving here and there. The rest is just like, it's like that. Okay, so let's go. Now, you learn about atom, you learn about just now electron. Sometimes you heard about ions. This is quiz, this is bonus time. What is ion? Raise your hand, raise your hand. Raise your hand, raise your hand. If not, I don't care. Okay, Yasmin first. Yasmin, what is ion?
An atom or molecule that has net electric charge.
Having what? Net electric charge?
Yes.
Having what? Sorry?
An atom or element that has a
Net
net electric charge.
electric charge. Okay. Net electric charge. Okay. Okay. So Yasmin Yasmin one. Okay, so ion is basically this thing. Atom, if you look here, the idea is this. That's why difficult. I need to go there and then I need to be here. So it's difficult. So you can see. Okay, if you look before, you can see this thing. In the middle, you have proton, you have neutron. Proton is the proton is the black one. The neutron is the white one. The green one, the turquoise one, is the electron. So you can see, if let's say, if you look here, the number of proton, there are 6 plus here, and also there are 6 negative there. So negative and plus in because negative and plus here, the negatively charged electron is negative charge, proton is positively charged. So they are attract with each other. Negative, positive attract, right? Different electrical polarity attract. So when they attract, that's what makes this electron cannot go out. Okay, and because the number of the positive is same with the number of the electron which is negative charge, they cancel each other. So the electron become neutral. The electron become neutral. But in one case, if let's say you kick out this thing, you kick this out, so this carbon atom will deficient in electron. Okay, so it's not balanced. The charge is not balanced. So you have carbon. If you kick out, it become carbon plus. This is not right lah, but anyway, carbon plus. This is basically if carbon lose one electron, and then you have, if let's say instead of losing, another electron come here, zap. There are 5 electrons, so that's what we call carbon negative. This means that carbon receive additional electron, 1 electron lah, electron. So when you see the salt, when you see salt, garam, salt is what? Salt is basically sodium chloride. When you put in water, what happens is basically this salt is deassociate, breaking, it break. Okay, so it break to Na and Cl, Na plus and Cl, what we call Cl minus. So this is iron lah. Okay, the reason why this is like this, okay, because Na and Cl, so Na here mean that this sodium atom have less, what we call, sodium berapa? 3. Sodium is 1, 2, 3. 3. Chlorine is 1, 2, 3, 4, 5, 6, 7. So this is chlorine. This is center. This is the nucleus. What I show you, I think you can see or not at the bottom. So you can see the sodium. Normally they like this. This is normal sodium. You have like extra 1 electron in the valence shell. Chlorine normally in the what you call neutral condition, it have 1, 2, 3, 4, 5, 6, 7 electron. Betul tak? Saya pun tak ingat. Let me check. Okay, so you see sodium 11. So mana tu? So 281. What does it mean is that it's like this lah. Meaning that you have another one lah. You have another what we call, Yasmin, can you see at the back here? Okay, meaning that this is 1, 2, 3, 4, 5, 6, 7, 8, and then there are 1 here. And then sodium, chlorine, they have 17. Banyak pula nak kita. So you have something 1, 2, 3, 4, 5, 6. So chlorine is what? Chlorine. Let me check chlorine here. So chlorine you get 287, meaning that the first s orbital is 2, so that's why 2. The second orbital, the p have 6, 8. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 8. And then the last is 7. So you can see this thing is normal, is neutral, because the amount of the electron is the same with the amount of the proton. So the charge cancel out. Okay, but when this meet with this will sort of like give this thing to here lah. So it become a compound. Lah. This is ionic compound. Okay, we will talk about bonding later on. But just to say that when you try to sort of like dissolve this thing is okay, neutral. But when you put in water, it will dissociate. When it dissociate, then this thing, they associate like this lah. So this is basically less than 1 electron than normal lah. Because normal they have electron. But when they make compound, this electron goes to this, go to Cl. So when you put in water, this will be deassociate. And this itself is not what we call not a stable sodium. Because stable sodium, they must have equal number of electron and proton. But here, the number of proton, the red one here is berapa? Is 11. Is 11. But here is 10 because if you calculate, betul ke 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 10. Okay, so that's what does it mean by ion lah. Okay, next is mana ni? Okay, so that is ion. Okay, proton. The proton in the middle here define what is the proton here. Inside here, the proton define the atomic number. If the proton is 1, then the what we call the atomic number is 1. If you look here, you see here hydrogen. If you look over there, the hydrogen they are 1. So this atomic number, So meaning that there are only 1 proton. If you go here, let's say iron, you have 26. So the number is 26. The atomic number is 26. It also means this iron has 26 proton in the middle. Okay, 26 proton, and to make it stable, it also have 26 electron. Okay, 26 electron. Okay, so that is the thing. And then, okay, so now atomic charge, the one that I just discussed just now. Proton is positive, neutron is 0, is like neutral, electron is negative. Both proton and electron has the same magnitude in terms of charge, just opposite sign. That's why even though proton is much bigger than the electron, both of them in terms of charge is similar, same magnitude, just opposite sign. That's why if you have 2 proton and 2 electron, even though the size is different, but the charge is equal in terms of magnitude, and it's different size. The proton is positively charged, the electron is negatively charged. So when the same charge, the opposite charge combine, it cancel each other because the magnitude is similar. Okay, so this is coulomb, coulomb. 1.6 times 10 to the power of negative 19 coulomb. Okay. Okay, now we talk about electron, we're done with the electron, we're done with the proton, and then we talk about the neutron. Okay, neutron, the neutron here, normally, they have the same number as a proton. Okay? Neutron normally have the same number with the proton. But neutron does not need to be the same amount of proton. For example, if you look, let's say I go here, hydrogen, carbon, gold. Okay? So let's see hydrogen there. Look at over there. Look here. So how do you know how much proton here? How do you know how much, not proton, how much neutron here? You know this is proton. You know this is electron. How do you know about, neutron? How do you know from this? Okay, from the mass here. Because the idea is this. The mass of the proton and the mass of the neutron is almost equal. So if you have 1 proton and then 1 neutron, the mass more or less become 2, roughly 2. Okay, so we talk about mass later. But here you can see, hydrogen have 1 proton and 1 electron. It should be 2, right? But then, why the mass is 1? So that's the thing. So this means that hydrogen having a proton, having the electron, this is proton, I put plus. But no electron, no neutron. There are no neutron. They have proton, yes, this is proton, and this is electron. So hydrogen is like this. So there are no neutron. Okay? But if you look at carbon, carbon here, you can see carbon over there, So you can see there are 6 proton, there are 4, 5, 6 electron. So 6, 6 become 12. So that means this carbon, they have 6, 1, 2, 3, 4, 5, 7, 1, 2, 3, 4, 5, 6. Plus, 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 plus. And then you have 6 neutron. 1, 2, 3, 4, 5, 6. Okay, neutron. And also, mana rate saya? And then rate for electron, you have whatever around here, they are, inilah, according to the orbital, there are another 6 electron. So you can see the number of electron, proton and neutron is same. Okay, that's why, and the mass for this proton and neutron is more or less the same. So that's why it becomes 12. But if you look at the gold, okay. So gold have 79 proton. If you look here, you don't need to calculate lah. Because why? Because the proton need to have the electron must be in the same number of the proton in order to make it neutral. So this 79 lah. Okay, because if this is not 79, then they become ions. Here it's not ions. It's all stable. So 79 proton, 79 electron. Tambah berapa? You add together how much? How much? 1, 5. 79 plus 79. 79 plus 79? 158. But you see the, what we call the weight here, alamak, the weight here is around 197 lah, 197. So somehow they are extra, right? So if you calculate, this we know, number of proton will never change. Because number of proton define the atomic number. Okay, so number, let's say this is a proton. So proton is this, 79. But the neutron, we don't know. This is not 79 because when you see the weight is 197. So 197 minus 158, what you got? Berapa? Calculator juga. How much? 178 minus 158. 39. Okay, 39. So there are 39 extra. So 39 extra here must be proton. Must be neutron. It cannot be proton. Because proton is fixed. Proton define the number. Okay. So basically 39, they plus here. Plus 39. So then you get 197. So the number of what we call the number of neutron there is 79 plus 39. How much? 100? 118. So as if now, not as if, it's actually, you have proton like this, proton, and then there are a lot more neutron. There. So that's what happened to gold. The reason is why? Why is that? Why the bigger, if you look, if you try to go further, you will see the number of proton keep increasing. Why is that? If you look at the beginning, no need neutron. Go to the carbon, same amount of neutron. But if you go become bigger and bigger, the what we call the number of neutron keep increasing. Why is that? Why? Anyone? Bonus. Cepat. Jawablah. Bonus. Cepatlah. Salah tak dapat dah. They are gas? No, because gold is not gas. Okay. Yes? Sorry? The size of the atom is increased. Actually, size of the atom increase doesn't answer that question because the size, if you look the size, if you see the size, if I go to the size here, size, radius here. So if I click here, you can see the darker one is bigger. So if you see the size is keep increasing here, so in fact, if you look here, the size keep decreasing, in fact. So something that is weird happening. Okay, sorry?
Maybe to keep the proton at the center from
Attract from the electron?
To keep the proton together with the neutron at the middle of the atom.
No, but okay lah. You sama siapa? Dapatlah 0.5. Apa nama? Ikram 0.5. The idea is this. you need to understand the proton is positive. Proton in the middle is positive. If you think about it, positive should repair, right? It should not be like this. So why don't this proton in the nucleus, the proton clump there? The reason for that, this is more like a fundamental force of the universe. There are 4 fundamental forces of the universe: the strong force, the weak force, the what else? The electrostatic, the electromagnetic force, and also the gravity. Okay, the strong force is what bind this proton in the nucleus. The strong force. So you can find strong force there. So meaning that they are what we call, this is more like physics. They are sort of like the particle, the gluon, who is like binding this proton together. Okay, so because of strong force. Okay, the thing is, when you are become bigger, the proton become bigger. The electrostatic repulsion between this thing is become a little bit, it becomes stronger and stronger. Even the strong force cannot hold it. So that's why they need proton, they need neutron. Neutron as if like a glue that hold them together. Okay, so the bigger they are, the bigger the atom, mean that the more proton inside, it will make this thing unstable, because the repulsive force between positive and positive can sort of like can overcome the strong force. That's why you need the more neutron. And now, about the size, why here is become smaller, why this is bigger? Why? Why this is bigger? The size, the concept of size is basically this. You have the, the size of an atom is basically you have nucleus, and then you have the, what we call, the electron. So the size is basically the diameter lah, the diameter here. So the question here now, why if you go bigger and bigger in terms of proton, because go here is bigger, right? 77, 78, 79, 80, 81, 82, 83. Why then the size here become smaller than this?
Because the force of
Wonder why? Sorry?
attraction between the nuclei
And?
and the electron increase.
Yeah.
The size of the group decrease.
The size of the group decrease.
The size of atom
The size of the atom?
decrease.
Decrease. Why?
Because the force of attraction between the nuclei and electrons increase.
Yeah. So what's your name? Shadi. One. Okay. So the idea is this. Remember, this thing is the same period. In the same period. The same period. What does it mean by same period? Is this. If you look, if I go to the properties here, series. Let's say here. Look at the number here. Look at the number there. Look at the number here. Look at the number here. If I go to the period number 1, there are only 1 electron. If I go period number 2, there are 2 level. The size, meaning that, remember this thing, this is 1, this is S, this is P, right? This is another S. But P lah, this P. This is basically SP. So you know we talked before when you go if you go to period 3, they have 3, meaning that it become bigger. The size become bigger lah. The size of the orbit become bigger. There are 3 orbit. If you go to this thing, they become 4 orbit. But if you go along the period, it's the same. 4 orbit, 4, 4, 4, 4, 4, 4, 4, 4, right? There are 4 orbit. If you go to the 5, you get 5 orbit. 1, 2, 3, 4, 5. 5, 5, 5, 5, 5, 5, 5, 5. You go to the 6th period, you have 6 orbit. Meaning that 6 orbit, meaning that much bigger lah. So if you compare in terms of radius, if you look here, this thing will not, this cesium is smaller, is bigger than the gold, is because first, this thing, if you look here, they are in the same period. So they are 1, 2, 3, 4, 5, 6, there are 6. There are 6 orbit lah, 6 orbit. So the amount of orbit is the same. But then, because of this gold, as we learned before, they have more neutron. They have more proton. Because they have more proton, they will attract the electron much further. Much nearer lah. So the effect of attraction is sort of like shrinking the size of the orbit lah. So that's the reason why the gold have less size than the cesium, even though the proton number for the gold is higher, because the higher number of proton meaning that the higher power to attract the electron. The influence of the attraction is much bigger than this electron size lah. Okay, so that's the thing. Any question now? Any question? No? Okay. Okay. So you can see proton, neutron have the same size, same mass. So we see larger atom, meaning that more neutron. So that's what we discussed. Okay. Atom is mostly empty space. Atom is mostly empty space. Okay. Hydrogen atom diameter, let's say this hydrogen diameter is 1 angstrom. Okay, convert this to, this is bonus. 1 angstrom, how many meter? Raise your hand and answer. 1 angstrom, how many meter? Raise your hand. You cakap tak dapat. Raise your hand. To get 0.5, this is 0.5 only lah.
0.1 nanometer.
No, I said in meter. In meter.
1 times 10 to the power of negative 10 meter.
Share lagi 0.5 only 0.5 only. So angstrom is basically 10 to the power of negative 10. Okay? Meter. 1.7 femtometer in nanometer. In nanometer, how much? 1.7 femtometer, how much? 1.7 time? Salah. Because that is femtometer. Negative 14. Negative 14. Because femtometer is basically 1.7 times 10 to the power of 15. This is femtometer. Femtometer. So nano is basically one level below femto. I asked you to read about this thing, right? So hopefully you get the idea lah. So this is 1 femtometer is basically 1.7 times 10 to the power of negative 15. In order to make it to nano, you need to remove 3 magnitude lah. So 1.7 times 10 to the power of negative berapa? 40. Berapa? How much? In nanometer. This in nanometer. How to do this in nanometer? Tadi betul ke tadi? Salah. Salah tak apa lah. Negative 6 negative 6. Okay, we do calculation because this calculation is important. Okay, so look here. Okay. 1.7 femtometer. 1.7 femtometer times. Okay, 1 femtometer is basically 1 times 10 to the power of negative 15 meter. That's right. Okay, times, because you want to, now you can cancel femto. So now you want to make it into nano. So how to do that? You want to meter, let's say 1 times 10 to the power of negative 9 meter, that is equal to 1 nanometer. So you can cancel this and this lah. So kira berapa? So 15 minus 9, how much? Negative 6. Salah kan? Dia betul. You salah. So basically 1.7 times 10 to the power of negative 6 nanometer. Okay, I think yang salah saya rasa nak lidak mak. Tak lah. Okay, you name, what's your name? Daniel. Daniel is 0.5 lah. 0.5. Okay, anyone can answer this question will get 1.5. Come in front and say lah, or just raise your hand lah. If let's say, okay, the question is this, because this is calculation. You are engineering student, so you need to know a little bit about calculation lah. Let's say, given this info, let's say this is the proton of the hydrogen atom. How far electron will be? Because remember, if you look, mana madam saya? Kira lah dulu. So if you look here, let's say the proton here, hydrogen only one proton. And then the size of the atom is basically from here to here. Okay? So let's say this is as the size of a tennis ball. Tennis ball. The question now, how far will be the farthest electron? Faham ke tak? Let's say this electron, hydrogen atom, the nucleus, the proton is magnified as big, this big. So when you magnify something, the other thing magnify. The size also magnify. So how far is the farthest electron will be? Meaning that how big is the atom? Because atom meaning that everything. You have the proton, you have nucleus, you have electron. Okay, so given this, what we call, this situation, this case, how do you calculate how far the electron will be? Whoever can answer this, get 1.5. Huh? How far the electron will be? Come in front, show. Huh? Whoever raise your hand and give the answer, get it. How far is the atom? Basically, how big is the atom lah, or how far the electron will be lah. So we want to see now what is the radius from middle to here. How far? How far is the thing? How far? How big? Let's say I hold this tennis ball. Let's say this is the atom. This is what we call the nucleus, the proton of the hydrogen. So where I can find the farthest electron. So that's what does it mean lah. Ini yang betul-betul punya. Ini yang actual punya. So the atom diameter is 1 angstrom, meaning that the atom, this atom, 1 angstrom. Then in reality, the hydrogen, this thing is 1 angstrom. This thing is 1 angstrom. And this thing is basically 1.7 femtometer. So now, if this thing become as big as this tennis ball, which is 6 centimeter, so how far now? How far? Instead of 1 angstrom, how far now? Okay tak? Who cannot understand the question? Yasmin, faham? Faham kot? Faham? Nama siapa? Danish, faham? Soalan faham? Tak faham? Kurang faham. Okay, let's say the hydrogen atom tu yang sebenarnya kecil je, tak nampak kan? Dalam hydrogen atom dia ada electron and also the proton, nucleus tu kan. Kecil tak nampak kan? Bayangkan you boleh besarkan nucleus tu sebesar ni, nucleus saja. Apa yang akan jadi pada dia punya the total itu. Itu maksudnya. So this test you engineering lah, proportion and so on. Anyone? So I think this last lah kot. Malah nak tambah. Banyak lagi ni. 1 page only. I have 4 page. 1 page only. It's okay lah. It's okay lah. We slow and steady lah. Anyone? 1.5 mark Depan Yasmin siapa? You. Depan you lah. Siapa nama? Nasha. Nak jawab? Rafiq nak jawab? 1.5. 1.5 is big 1.5 point can make a difference. Okay? Because remember over time, along the way, along the semester, maybe at the end of the semester, maybe we are quite hectic. So I don't have this bonus mark time. Okay? So use it while you can. So I think this is the last question lah. Last question for today lah, because I think we need to. I give you another 1 minute. No, if no one answer, not I think you need to go and just. You don't understand the question?
We just the 1.7 is like the size of
the actual thing. The actual atom. Okay, the actual hydrogen atom. The nucleus is 1.7 femtometer. The atom itself, because nucleus is just one part of the atom, right, in the middle. But the atom is all the thing. The nucleus, the electron, you can see the electron cloud, right? So the electron, the diameter of, people say the diameter of the atom, it mean like the everything, the nucleus and the electron. Okay, so the everything, when people say this hydrogen atom diameter 1 angstrom, meaning that all this thing, hydrogen atom. But you know, inside hydrogen atom, they are nucleus, they are proton. So that proton, the size is 1.7 centimeter. The diameter lah, the diameter. The hydrogen atom, the diameter is 1 angstrom. My question is that, what if you can make this bigger? What if you can make this as big as this? How big is the overall atom? Understand or not, the question?
So like 1.7 would place it with like 6 centimeter, right?
Yeah, that's what I want to see, how you do it. The answer. Yeah.
Sir, is the answer 3,000?
No, dia dulu.
Is the answer is in angstrom?
No, in whatever lah, in meter.
3,530 meters.
Sorry?
3,530 meters.
3,530 meters. Okay. So that is basically right lah. Okay, I want to show you how. Okay, how. This is the concept of proportion. Actually, it's simple, yeah. It's simple. It's simple. For example, the ratio. Okay, the ratio. Okay, look here. The ratio between this, you need to find the ratio lah. For example, 1 angstrom is basically 1 times 10 to the power of negative 10. Okay, and then you find the ratio between this and this. So this 1.7 times 10 to the power negative 15. The ratio is basically around what? 60,000, right?
No, 3.53 times 10 to the power of 10.
No. The ratio.
I don't know the ratio.
64,000.
64. Let's say 60 lah. 60,000. So the difference between the size of this and this is 60,000. So now, if you have the size of this is 6 cm, which is 0.06 meter, right? You just times 6,000 lah, 6,000. So you get around how much? 36, roughly like that lah. 36,000 meter. 1,000 like this meter. 36,000 meter. So because this is in here ke? Time this how much? 36,000 meter lah. 36,000 meter. So equal to 3.6 kilometer. Okay, 3.6 kilometer. What does it mean by that? If let's say I go to, if I go to Google Earth, explore Google Earth. Okay, explore Google Earth. Like it's loading first, and then okay. So while it's loading. Okay, so let's put here how to do this? IUM gombak. Okay. Okay, let's say you are here. Where is you? So let's say here. Let's say this, you are here in this and then let me take this thing. So imagine now I am here. I holding this thing. What we call tennis ball. If this is a real hydrogen atom, you can find the what we call the farthest electron here. So this is, you can see there. So to the stadium is around 900, 800 meter. So if you go further, twice this thing until here, that is only a radius. So basically, you can find the farthest atom here, you go to the stadium and twice you walk, you get here 1.7, and then you times 2, you get 3.6 lah. Because this is radius. Because the atom is like a 3D, going there and going there. So here, if, for example, the 3.6 km is basically this, 3.6 km. So here to here is 1.8 like that lah. So that's why here, the farthest electron you can find is outside UIA, like that. So meaning that this is a nucleus, this big, and whatever in the middle is just empty. Empty. Okay? So it's mostly empty space. So we start today, we will continue later lah.